Hi, my name is Christopher Tull, and I'm here representing the California Data Collaborative, which is a coalition of municipal water utilities dedicated to sharing data to inform better, smarter water management. And I'm here in particular to talk about a project that we recently completed, estimating the water savings from residential turf removal. As many of you probably know, for the past several years, California has been in a severe drought. You can see on the left-hand side of the image the U.S. Drought Monitor status for California from 5 days ago. You can see that this is still an issue and the drought has not subsided. And because of this focus on the drought, a lot of water utilities have put a lot of effort into encouraging water conservation, and in particular, in cutting down on outdoor water usage, which accounts for approximately 58% of residential water use in California. And a big part of this strategy to reduce outdoor water consumption is encouraging turf removal, they oftentimes through rebates. And so basically what they do is they will say, oh, if you remove you remove your water-intensive lawn and replace it with some sort of drought-friendly landscaping, and then they pay you some amount of money per square foot of turf removed. So the goal of this work was to get an idea for the water savings, sort of an empirical idea for the water savings in order to estimate the value of this investment. So the basic approach is sort of a modified difference in differences approach, where we match, and then we model, and then we merge. The match portion, we take households that are similar to the treatment household, so the treatment household that removed removed a portion of turf under a rebate. We find households that are similar to them, and then we use those as inputs into a Bayesian structural time series model that creates a synthetic control that serves as a counterfactual for how much water the treatment household would have used had they not participated in the turf rebate. And then we merge these individual household level estimates to get an overall estimate. The whole analysis was done using the R programming language, specifically the market matching packages, causal impact package, and the metaphor package. So the first step, the matching, the basic idea is to find, as I said, some similar control households, some households that are similar to the treatment household in some way, except that they didn't remove their turf. So we first narrow down the list of possible controls by limiting to only the zip code in which the treatment household is. And then we create a similarity ranking, two different similarity rankings initially. The first based on the Pearson correlation, so tracking how the time series so we're looking at the time series in the pre-rebate period before they remove their turf, with a minimum of 2 years of water use data monthly. And the Pearson correlation will tell you how they increase or decrease in common. And also, we create a second ranking with the dynamic time warping distance, which measures the absolute distance between the points along the warping curve. And then to combine these, we basically create a weighted average of these two rankings and then select the top 6 most similar households. The top 6 households that had the most similar water usage patterns in the pre-rebate period. And we use those 6, quickly you can see this, this is what this looks like in practice. The light green line that sort of flattens out after the dotted line is the household that participated in turf rebate, and the other lines are the water usage patterns for the chosen control households. And you can see that after the rebate occurred, this particular household sort of seems to have stopped outdoor watering altogether because their curve sort of flattens out and doesn't have any seasonal trends. So those 6 control households are then fed as input into a Bayesian structural time series model to create our synthetic counterfactual. And the model, this is what the model looks like. And there's the 2 main points that are important here are the regression component, z of t, and the local level term, mu of t. And the z of t is the sort of linear regression term that captures the static linear relationship between the controls and the treatment household in the pre-rebate period. And then the local level term captures local linear trends and enables the model to react to more variability than if we were just tracking the static portion. And this model, another reason this model is important or is appealing is because so it's a difference in differences approach in that if we were just strictly modeling based on, say, weather and landscape area and other sort of more static factors, we wouldn't be able to account for large exogenous shocks like the 2015 mandatory water reductions that took place here in California. But with this method, ideally we should be able to account for that because the control households will also reduce their usage in the post-rebate period, and sort of the savings that are left over are what we attribute to the turf rebate. You can see in the images here, the red line is the predicted counterfactual, and the blue line is the actual observed water use. And so you can see that these lines diverge in the post-rebate period. In these two examples, the water usage is significantly less than we would have expected if they had not removed their lawn. And so we take the difference between these two curves and attribute that to the water savings of the turf rebate. So those two steps give us an estimate of the household level water savings for each individual household. But in order to get an overall estimate, we use a, we use a mixed effects meta-analysis model where we're able to take not only the water savings estimates, but also the credible intervals produced by the Bayesian structural time series model and produce a sort of weighted estimate for these savings. So we have our estimated water savings as a dependent variable, and these here as our independent variables. Most of the responses are pretty intuitive. Evapotranspiration, for example, is negative, meaning more water savings. So if hotter, drier weather, you save more water. We then take this model and predict it on all of the households in our sample and then take the mean of those estimates in order to come up with our overall estimate of 24.6 gallons saved per square foot of turf removed. But that doesn't really tell the entire story. It's more interesting, honestly, to look at the monthly savings for a couple of reasons. You can see there is large monthly variation with roughly double the savings in the hot summer months compared to the wetter winter months, which is intuitive if you assume that you're avoiding more outdoor water usage that would have taken place during the summer months than you are in the winter months. And this also is important to look at a monthly level because that's sort of the timescale that water utilities plan things. If they want to know what the revenue impact might be from investing in these water savings reductions, they want to know it if it's going to be different in the fall or in the winter from in the summer, for example. I'm going to step back 1 second and talk about the California Data Collaborative, the organization that I'm here representing. The California water landscape is very fractured. There's 411 major urban water retailers in the state. And so what we're doing is working with these staff at these utilities to integrate customer water use, so billing data from these utilities into a centralized water use database, and then providing them with analytics and tools to help them. As part of that, we're in the process of operationalizing this approach to other water conservation actions, not just rebates. So think marketing outreach or educational outreach, those sort of things. And in our phase 2, we want to make this centralized data store of water use available to academics and researchers who are interested in learning more about what works and what doesn't for water conservation in California. I'd like to thank utilities, our utility partners, for the funding and providing the data for this project. And thank you. Are there questions?